the isosceles triangle theorem is this. If I can prove, if I have a triangle that has two congruent sides, then I can prove that the base angles are congruent. So let's just start right there. So the isosceles triangle theorem is, if I have two congruent sides, two congruent legs on a triangle, then I can prove that the base angles are congruent. Does that make sense to you guys? So that's the theorem. So now let's prove that theorem. So to prove that theorem, what I'm going to do is I'm going to draw an isosceles triangle, and then I'm going to bisect that angle. And so if I say y, x, and z, and then I put b, and I say that these are congruent, I want to prove that y and z are congruent. So I have my statement here, and then my reason here. Okay? And the only other thing that I need to define is that xb bisects the angle here. So what I want to say is that, let me just write it down. xb bisects angle y, x, z. Now I could do a construction on that, right? We could take a compass out, I could construct it in a way that it bisects that. Okay, I'm not gonna. Just know that it does. And then the other thing that we're told is that yx is congruent to zx. So technically those are given to us, right? At least that's how it's drawn in the textbook. Okay? So now remember, what I want to prove, way down here, I want to prove that angle y is congruent to angle z. Okay? And so I have two triangles, and one thing I notice is that xb is congruent to xb. That's the reflexive property. In other words, this line is congruent to itself. We also know that angle 1 is congruent to angle 2. Well, how do I know that? That's based on the definition of a bisector, right? So what I have here is I have a side, and then I have two corresponding angles that are congruent, and then the side in the middle. So I have side, angle, side. So I could say that triangle y, x, b is congruent to triangle zxb. And that's based on side, angle, side theorem of congruence. And so since those two triangles are the same, then I could say with confidence, since angle y corresponds to angle z, that those two are congruent because corresponding parts of corresponding parts of congruent triangles are congruent. And that's it, we're done. So we've proven that. Right? So that's that one. Does that make sense?
Can't you just go straight from what was given to you? Can't you just use the isosceles triangle theorem and go straight into that? Because you already have the two sides that are in there.
Well, we know what the definition of an isosceles triangle is, but we have to define. See, when I say that they're that way, That's given to you. In other words, I think the question that she's asking me is, hey, since you know it's an isosceles triangle, can't you just by definition say that that's the case? No, because we are told we don't know based on what we see, right? We have to prove that it's an isosceles triangle. Now we know that because we started off with the definition of an isosceles triangle, right? So we were like, hey, if you have two legs that are congruent, then that's an isosceles triangle. But this is really the proof as to why it's isosceles. So we're defining what, well, this is really a theorem that shows the correlation or proves that if you have two legs that are congruent, then the base angles will be congruent. I just proved that. That's the proof. And then the converse would be the other way around. And it would be the same thing. So let's write that out. So the isosceles triangle theorem, if you have two angles that are congruent, or not two angles, two legs that are congruent, dot, 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 then the base angles are congruent, okay? Now the converse of this, is that if I have a triangle that has two congruent angles, whoops, not it, if, I wrote my F upside down. That's a new type of dyslexia. Alright, so now if I can prove that the base angles are congruent, then I can also prove that the two side legs are congruent.
So this is what you do when.
Now, and the proof for this would be very similar to the one that I just did. In fact, when we go to do, we'll actually do that. I'm going to redo problem number 1, and you'll see that we're technically doing the converse. Okay.
So these are in between these ifs and thens for this. You would put all these your statements in?
Yeah, all the statements. Yeah. So once we prove something, we can call it a theorem, right? So we're cutting out the middlemen, right? So what she's saying is, Mr. Adams, to show we did all this, right? To show, right? So this would be like, this would be like P, if P, then Q, then R, then S, then T, right? So we did all this stuff here, and really what we did when we write a proof, it's like saying, if P is true, then Q is true, then R is true, then S is true, and T, right? Well, this is like our P, and this is like our T, right?
Yeah.
We don't need to write the proof every time. We just accept it. We just got to prove it one time, and then we can, now that we've proven it, we just accept it.
Okay.
And then this is like our T, and this is like our P. And I'm not going to go through, well, we'll go through the proof, but we won't really go through the proof. Well, it's not really the proof. We're just going to actually do the problem.
So could you, like, where you take a whole proof, like the T-chart, the statement, and the reason, you take them all, like for this one, you can just kind of take it all down and do just P and T, right? Like what you did for this one.
Yeah.
Then can you do that for any, like, T-chart statement or reason? Like,
Yeah. Yeah. Once we've proven something to be true. See, that's the beauty of logic and geometry. Once we've proven something to be true, we could just accept it and use it. All right? From here on out. Like earlier in the school year, we said that the sum of the interior angles of a triangle is 180. We've proven it once. We don't need to prove it every time. We just say it, right? And that's a theorem. The theorem is that the sum of the interior angles of a triangle will always add up to 180. Do we need to do that same proof every time? Nope. We don't.
So it's pretty much proofs instead of proofs.
Yeah. That's why when we started this, we talked about the law of detachment and syllogisms, right? The law of syllogism. we're using the law of detachment and the law of syllogism basically to prove things. Right? So if P is true, that's why some of those given statements prove the validity, right? If this is true, is it true? Yes. Then the next step is true. Then the next step is true. Then the next step is true. Then our proof is true as well. Okay? But once we know that sequence of truths, then we don't need to go through it every time. We skip ahead, yeah. Yeah. Yep. Good. So now to see the converse in action, we're going to do this problem again a second time so you guys can kind of see it. So I've got this triangle like this, and it's drawn, well actually let's do it like this. And it's in your textbook like this, and we're given that this is congruent to this, and that this is A, B, C, and then D and E. And they want to know, this is the question, they want to know if AB is congruent to CB. And the confusing part about that is you have a tendency when you look at this, you're going to say, oh, well, somehow I've got to use this information to prove that AB is congruent. Actually, no. Because I have angle A here, angle C here, and then B. And if I go back to the converse, I can prove this, but I'm not going to write it all out. If I construct a bisector of this, then I'll have two congruent triangles, right? Because I'll use the reflective property, and I'll have two angles. I'll have an angle, and then two angles up here, right? And then this will be congruent to itself, so I have an angle side. So I proved that those two are congruent. Well, when I do that, then in reality, I'm going to prove this. Right? Does that make sense?